Today we're going to learn about a few more derivatives to add to our repertoire of basic derivatives that we need to know. And I'm not going to go through the proofs for all of these, but for this first one at least, I want to just kind of explain where this particular derivative is coming from. So now we already know how to differentiate y equals e to the x, right? If we differentiate y equals e to the x, um, we're going to get dy dx equals e to the x, right? E to the x is its own derivative. We know that. We also know how to use the chain rule with e to the x, right? It's kind of like saying y equals e to some function, which we'll just call f, would be um, e to the f of x times f prime. So that's using the chain rule. So here, if that f of x is sine x, when we differentiate that, we're going to get dy dx equals e to the sine x times the derivative of sine x, which is cosine x. So these are two derivatives that we already know how to deal with. But what we don't know how to deal with is an exponential equation where the base is not e. So let's think about y equals 4 to the x. Here's an exponential function where the base is 4. And so I'm going to do a little mathemagic here to get us to the derivative. You're not going to have to replicate this, but I think you might find it a little interesting. So if I were to take the natural log of both sides, that would allow me to use a property that we commonly use when solving exponential equations, and that's the power property, which allows me to rewrite a logarithm that has an exponent in the argument as a coefficient. So I can rewrite this as x times natural log of 4. And so now natural log of 4 is just a constant. And if I wanted to differentiate both sides here, on the left-hand side, I would have to use the chain rule. The derivative of natural log is 1 over the thing, in this case y. So it'd be 1 over y times y prime. And I'm going to rewrite that, and you should probably get in the habit of rewriting anytime you have to do chain rule with natural log, as rewriting that prime or that derivative on the numerator. So y prime over y. And then on the right-hand side, we can use the chain rule here. The derivative of x is 1 times the natural log of 4 plus x times 0, right? Natural log of 4 is a constant, so that derivative is 0. If you already recognize the fact that natural log 4 was a constant, then you could have just differentiated this as natural log 4, right? Like if this is just like 3x and you differentiate 3x, you're going to get 3. So here, natural log of 4 is a constant. So we're just going to end up with natural log of 4. But I just want to show you the product rule in action to kind of explain why that is. So here we've got y prime over y equals natural log of 4. And if we want to know what the derivative of this thing is, we could multiply both sides by y. And you might be thinking, okay, well, we found y prime, but we have a y in our equation. That's going to be kind of annoying. So what we could do is note that y from the very beginning was 4 to the power of x. So we can rewrite y prime as 4 to the power of x times the natural log of 4. Just keep in mind, natural log of 4 here is a constant. So you might imagine that we could go through this process the same way, but instead of using 4, just using like any other base. So like if I start off with y equals a to the x, I could still differentiate both sides. I'm going to end up with a similar statement here, except this 4 would just be a. And then I'd have y prime over y equals natural log of a, and so on and so forth. And so we would have a generic derivative formula for anything to the x power. And so let's go ahead and write that down at this point. The derivative of some base to the x power is going to be that base to the x power times the natural log of that base. And that the natural log of that base will be a constant. So that'll be kind of like the coefficient of your exponential function. But yeah, so that's the derivative for an exponential function. So we'll go through a couple of examples here. Like for instance, we have y equals 3 to the x. The derivative is just going to be 3 to the x times the natural log of 3. Now we already know how to deal with y equals e to the x. We know it's just going to be e to the x, but let me kind of show you why it turns out that that's true. Using this derivative rule, we can say that y prime is e to the x times the natural log of e. And the natural log of e just simply equals 1. So 1 times e to the x is e to the x. And so this is kind of a special case of this exponential derivative. In fact, this is why we kind of call it out, because, or give this base its own name, Euler's number, e. Because it's the only exponential function that is its own derivative. So that's pretty interesting. Number 3, we'll go ahead and differentiate both sides here, but we're going to have to use the product rule. Okay, so this is actually a product rule, chain rule. This is actually not going to require that we do anything different than what we've done before. We can treat it like we treated y equals sine x up here. And so we'll say y prime equals e to the x squared plus 2x times the derivative of what's in the numerator here, 2x plus 2. Make sure you put parentheses around there. Okay, number 5. Okay, now we're going to solve a very similar problem here, but the base is going to be 5. Okay, so y prime is going to be 5 to the x squared plus 2x times the natural log of 5. Okay, so this is the sort of base derivative, but then using the chain rule, we're going to have to multiply that by the derivative of the inside. So that'd be this x squared plus 2x. So that'll be in parentheses here, 2x plus 2. So it's going to be solved very similarly to how we did the e to the x squared plus 2x. The only difference is you're not going to see the natural log of e written here because the natural log of e is 1. Number 6 will work just kind of the same way that we're working number 5 here. So y prime, I'm going to actually write it a little further down here. Y prime is 8 to the power of sine x plus x cubed times the natural log of 8. So you just kind of rewrite the exact same thing you started with, multiplied by the natural log of the base. And then we're going to multiply, using the chain rule, by the derivative of that exponent. So the derivative of sine is cosine, and the derivative of x cubed is 3x squared. Number 7, we're going to have to use the chain rule, where 5 to the x is our f, tangent x is our g. Okay, recall that if we find the derivative of a product, f times g, then the derivative would be f prime g plus fg prime. Okay, so on this one, the derivative of 5 to the x is going to be 5 to the x times the natural log of 5, okay, times g, so times tangent x. So that is just the f prime g. And I suppose I'm going to need to move this over a little bit to make it fit. Oh, nope, it's not going to let me do that. That's okay. I'll just rewrite it. Okay, so I'm going to scoot way back here. Okay, so 5 to the x times natural log of 5 times tangent x plus 5 to the x times the derivative of tangent. It's been a little while since we used that one, but it's secant squared x. Now, I suppose you could potentially factor out that 5 to the x as a GCF, but we don't really need to simplify that. Okay, so now we've added one more derivative to our toolkit here. We know now how to differentiate any exponential function, but we're going to add a few more here. The next derivative is going to be log of any base. So we already know how to differentiate the natural log of x, just as a little reminder, the natural log of x. We want to differentiate that. It's just 1 over x. But let's say the base was not e. Let's say it was some other base. In this case, base a. So the derivative of that is going to be 1 over x times the natural log of the base. Okay, it's almost like you can think of it as like 1 over x, which is your natural log derivative, times 1 over natural log a. It's another way you could think of it. But multiplying those together would result in what I've got here in the box. So let's run through a few examples here. Log base 8, if we want to differentiate that, we're going to get 1 over x times the natural log of 8. And that's your answer. It's really not much more to it. If we were to try to use this logarithmic rule, or this derivative rule on natural log of x, we already know what the answer is going to be here. But if we just follow this rule, and we get 1 over x times the natural log of e, you're going to see the natural log of e is just 1. So this is going to be equivalent to 1 over x, which is the derivative we already know how to do. Number 3, we're going to have to use chain rule here. So y prime is going to be 1 over x times or not x, sorry. It's got to be the thing that's inside there. So this sine x plus 2x times the natural log of the base, so natural log 7. Okay, then we're going to multiply that by, using the chain rule, by the derivative of the inside, which is cosine x plus 2. And I would recommend that you rewrite these logarithmic derivatives just as a single fraction here. When you use the chain rule and you multiply by this expression, go ahead and just multiply by 1. And normally I don't require you to simplify, and I wouldn't even take off points if you didn't do this. But most of the time, when you see these logarithmic derivatives on the AP test, they're going to be written in simplified form like this. So yeah, there we go. There's number 3. Number 4, we're going to use chain rule one more time. So y prime is going to be 1 over x squared plus tangent x times the natural log of the base here, which isn't written. Okay, no base written here. There's an implied base of 10. So natural log of 10 would go there. Times the derivative of the inside, which would be 2x plus secant squared x. And again, let's rewrite this with that 2x plus secant squared x on top. We'll just look a little better here. And there you go, there's a derivative. Number 5 says y equals log base 2. So our base is 2. We're going to set this up just like 4, just like 3. Y prime equals 1 over 2x plus 8 times the natural log of 2 times the derivative of what's on the inside, which is just 2. So I'm going to write this as 2 over 2x plus 8 times the natural log of 2. Okay, so far we've gone over 2 new derivatives, right? We went over the exponential functions with bases that are different than e, and we also went over logarithms with bases different than e. And so there's just three more here, and they're all going to be kind of together. And you might, want to flashcard your way through this because you are going to need to know these derivatives, but they're not going to be super easy to memorize. I'll post links on our website with proofs of these if you want to get a deeper understanding of why these derivatives are what they are. But these are all the inverse trig functions. So before I tell you what the derivatives are, I should note that there are two different, just like there's two different notations for derivatives, right? We've got the Leibniz notation and the Lagrange notation with the primes versus like the dy dx. And with inverse trig functions, there are also two different ways of writing the same thing. So I want you to be comfortable when you see either one of these. The inverse of sine can either be written as, like what you see down here, sine, almost looks like you're raising it to the negative first power, although it's just inverse notation. But there's another way of writing this, and it's arc sine. So these two functions are the same. They're just two different ways of writing the same thing. Same thing goes for cosine. This inverse cosine can be written like this, or it can be written as arc cosine. And that's going to be true for all of these inverse trig functions. So there's no guarantee on the AP test which of these forms you're going to see. I think it's going to be kind of a mix. So you want to make sure that you're comfortable with both of these notations. So let's go through the actual derivatives. We'll try a couple of examples. And that's going to be just about it for today. It's going to be a way shorter lesson today than the last class with those tangent line approximations. Okay, so for this first one, the derivative of the inverse of sine is going to be 1 over the square root of 1 minus x squared. The derivative of inverse cosine is going to be the exact same thing except negative. So negative 1 over the square root of 1 minus x squared. One way that I think might help kind of keep this straight is that if we just think about the derivative of sine, it's positive cosine. And if we think about the derivative of cosine, it's negative sine. So the sine's derivative will be positive, whether it's sine or inverse sine. And the cosine derivative will be negative, whether it's derivative of cosine or derivative of inverse cosine. Now the tangent one is going to be 1, the derivative of inverse tangent is 1 over 1 plus x squared. So a little bit different, kind of looks similar. I'm going to rewrite this inverse cosine, so separate that minus from the x squared a little bit. Yeah. Okay, so today you're going to learn, or we are learning 5 new derivatives. We've got the exponential functions, logarithmic functions, and these 3 inverse trig functions. So a total of 5 new transcendental derivatives that I'm going to start integrating into your homeworks and practice problems and notes. And moving forward, you can expect to see all of these kind of pop up here and there. So let's do a few inverse trig examples here. Each one of these 3 is going to use the chain rule. So wherever you see x in the actual derivative is going to, instead of writing x, I'm going to write like what's inside the function. So the derivative of inverse sine of 3x to the 4th, y prime, is going to be 1 over the square root of 1 minus 3x to the 4th squared. And then, of course, we're going to use the chain rule, so times 12x cubed. So just like with those logarithmic derivatives, I'm going to rewrite this as 12x cubed over the square root of 1. And I'm going to, just because this is going to be how it appears on the multiple choice items, if it's a free response, you can leave it like that. But if I square this term, I'm going to get 9x to the 8th. And this is going to be how you will see it more likely on a multiple choice item. Number 2, we're going to do this in basically the same way that we did number 1. We'll differentiate both sides and get negative 1 over the square root of 1 minus e to the x squared times the derivative of e to the x which is just, of course, e to the x. Oh, that e didn't come out. If I were to rewrite it, it would come out as negative e to the x over the square root of 1 minus e to the 2x. Anytime you raise a power to a power, you multiply those powers. So yeah, here is the simplified version of that. For arctangent, just recall that arctangent is the same as inverse tangent. So it's got the same derivative. So y prime is equal to 1 over 1 plus 5x squared, quantity squared, times the derivative, got to use chain rule, times 10x. So y prime is 10x over 1 plus 25x to the fourth. All right, so those are, one example of each. I just got really one last problem here. It says if f is arcsine, then what is the value of f prime of root 5 over 3 in simplest form? Okay, so, well, if this is f, then we know f prime is our arcsine derivative, which I'll pull it up here so you can just see it. It's going to be 1 over the square root of 1 minus x squared. So if I want to try to evaluate this derivative at root 5 over 3, so f prime of root 5 over 3, that's going to be 1 over the square root of 1 minus root 5 over 3 squared. Okay, we need to square that fraction, and I'll just do that first. So 1 minus the square root of 5 squared is just going to be 5, and 3 squared is going to be 9, so 1 minus 5 ninths. 1 minus 5 ninths is going to be 4 ninths, because 1 is 9 ninths, and 9 ninths minus 5 ninths is going to be 4 ninths. And then we could take the square root of both 4 and 9 individually. Square root of 4 is 2, square root of 9 is 3, and 1 divided by 2/3 is going to be 3/2. That'll be your answer for number 4. So just to summarize today's lesson, we've got 5 new kids on the block here, and while you do your homework, hopefully you'll start to commit these different derivatives to memory. We've got logarithm, specifically with any base, rather than just e. We've got exponential functions. We've got inverse sine, inverse cosine, and inverse tangent. So these are going to be our 5 new derivatives. And what I would like you to take a look at is down here on your own. See how many of these you know. Each one of these, except for maybe number 8, are ones that we've been dealing with quite a bit. So I just clipped this from a textbook that I have, and it's just a list of all the derivatives we've gone over so far, except for maybe 8, although I think we may have briefly mentioned it, but that was not one that we really spent a lot of time on. Yeah, so challenge yourself. You maybe take out a sheet of paper and write out the first part of all these derivatives and see if you can't come up with them yourself. Just to kind of test yourself, because at the end of the day, you're going to need to know all these. So that's it for today. You guys go ahead and you can start working on your homework. And yeah, have a great day.